Now, one of the important factors is the ability to transform algae into oil, because we always need more energy in our industrial economy. And we have a few slides that illustrate this, because many people might not know how algae becomes oil. Can we see the next slide, please?
And so this slide demonstrates, Marty, sort of how we grew algae in small containers to develop the tools for monitoring the growth of the algae and monitoring all the conditions within that environment where the algae are growing.
Okay, we have another slide which shows harvesting the algae. Like, how do you actually get the oil from the algae? So this picture here, what are they doing with the algae that's going to result in oil production?
So the big problem with these microalgae is that they're suspended in the water and we need to get them out. And the good news is that there's a lot of technology already existing for taking tiny particles out of water. And what this picture shows is how you can take these microscopic cells out of the water. And we concentrate them, and then we either dry them and extract the oil. I think that's shown in the next slide.
Okay, can we see the next slide? There it is.
And so there you can see the algae dried in that glass jar, and then we extract the oil either using a solvent or just by squeezing the algae and getting the oil out. Now, what a lot of people don't realize is that most of the fossil oil that we're currently harvesting from the deep earth or under the oceans came from these similar kinds of microalgae that existed 300 million years ago and were buried about 50 million years ago. And we're seeing the same kind of high production of oil from tiny microalgae that exists today.
So this is pretty much the same quality of oil that you would get if you drilled in the ground?
It's actually a better quality than oil, because a lot of what goes on in the ground at high temperatures and high pressures contaminates the crude oil. And we can make a kind of almost vegetable oil grade oil. The big problem is figuring out how to make enough of it.
Well, how big would one of these farms have to be in order to be economical?
Yeah, well, that's sort of the probably more than $64,000, probably many millions of dollar question. What we're looking for in the global initiative is building a demonstration project of about 1 acre. And that would be a proof of concept scale where, yes, indeed, we can get all the parts of the system to work at 1 acre, and it would be modular. And then we would iterate that 1 acre, making multiple versions of it. In San Francisco, the wastewater that's produced, as an example, is about 65 million gallons a day, which is enough to fill 1,280 acres of an omega farm. And that 1,280 acres would make between 2 and 6 million gallons a year of biodiesel.
Now, does algae turn all of the wastewater into more algae, so essentially all the waste just disappears and is transformed into plants?
Yeah, so that's a really important question, Marty, because what the algae do is they not only extract the nutrients that are in the wastewater, which is the nitrogen and the phosphate and the potassium and many of the other elements, but it turns out that they also can treat the wastewater for pharmaceutical compounds. They remove caffeine, they take out the heavy metals. So they do really good things in cleaning up the wastewater. The omega process takes that water 2 or 3 stages farther by treating the water using forward and reverse osmosis in a highly efficient manner that allows us to make this wastewater into drinkable water.
I think we have one more slide in this series of slides. Can we see that next slide, please? Okay, so this looks like a couple of specific elements. This would be a big array in the final farm, but those look like plastic tubes. So how is that really working? Did the algae grow in the tubes?
Yeah, so Marty, those are flexible, inexpensive plastic. It's linear low-density polyethylene. It's the same plastic we make greenhouses out of right now. Very UV-resistant plastic. It's very flexible. It's very inexpensive. And most importantly, lots and lots of it is available and can be made and recycled very effectively. We make those tubes, they extruded those tubes, and we grow the algae inside those tubes. And then we have to sort of maintain the algae culture using different technologies. But that is a representation of what a typical tubular system works could potentially look like, and it would be easily cleaned with little sponges that run down the inside, and can be made into many, many iterations to be able to make this system.
So do you start with a little bit of algae, and then the algae expands as it eats the sewage, and then when the tubes are filled with algae, you harvest them and then start over?
Yeah, sort of. We actually harvest them continuously. So the algae are circulating through those tubes, and they circulate through what's called a gas exchange column. And then in the gas exchange column, we also harvest them. So we harvest them continuously. We add wastewater regularly, so we're sort of feeding them all the time, and they're growing and growing in the wastewater. We also feed them carbon dioxide, which, as I mentioned in the video we just saw, is a greenhouse gas that is really good to tie it up in algae rather than let it loose in the atmosphere where it's warming the atmosphere.
Now, do you pump carbon dioxide directly into the tubes, or is it just pulling carbon dioxide from the atmosphere?
We pump carbon dioxide into this column where we can exchange the gases. And this allows us to feed the algae with carbon dioxide that would otherwise go from something like flue gas from a chimney into the atmosphere. Instead of dumping it into the atmosphere, we feed it to the algae.
Does it take a lot of energy to run the algae farm? Because it has to produce more energy than it consumes, otherwise it's not very valuable.
Why, Marty, that's exactly the rub. You need to be able to get an energy return on energy invested that's greater than 1, or else why do it? And in the Omega system, we've integrated it with solar energy, and we've also integrated the idea of using wind or wave energy. But the solar energy is more than adequate to provide the energy that we'll need for growing the algae. And in that case, we can raise the energy return on energy invested above 1.
Is there any specific kind of algae you use which is superior for this purpose than other algae? I mean, do you have to pick the right algae?
Yes, that's true. We want to get the right types of algae. We've actually just used algae that grow naturally in the wastewater. And keep in mind that our system, the Omega system, is a freshwater community of algae living inside those tubes, and they're surrounded by seawater. So if our system leaks, the algae die in the surrounding water, so they can't become invasive species in the marine environment. So we're not too partial about what algae grow in our system, as long as they grow on wastewater and they die in seawater.
What are the remaining technical problems that have to be solved before this can really be rolled out as a working project?
There are a number of problems. The biggest problem, though, really is scaling. And we need to test this at larger scales. The Omega system that was tested as a NASA project and a California Energy Commission project was only done up to about 450 gallons. We need to go to thousands and even millions of gallons. And that scaling issue needs to be resolved. There are many other social problems in terms of, so where are we going to be allowed to do this? And what about wind and waves? And what about currents? And so we need to identify protected bays.
Well, you're right. You live next to San Francisco Bay. That would seem like a good prospect.
Yes, and there becomes another social problem. How do you get permission to use San Francisco Bay? And how long will it take you to get permits? And then if you did get permits, what about legal issues? And so what about litigation that people don't want a not in my backyard mentality? So we've been looking globally for solutions, hence the name, the Omega Global Initiative. And it could be that the U.S. won't be an early adopter because of some of these restrictions that are just legal issues.
Is it very capital intensive to begin with? I mean, it takes up a large space, but the basic materials seem fairly simple.
Yes.
A lot of plastic tubing.
Yes. No, that capital costs are reasonably low. The biggest hurdles that we have now have to do with building the offshore infrastructure and coming to terms with building a structure that's stable and robust in the marine environment. The biggest cost is not going to be the plastic. Pumps are one of the costs, but the big issue now is getting the first example, right? Once we build one, then everybody else will say, oh, we can do it better than that. And then we'll have a bunch of people trying to develop this technology. The reason this is important is to get a first example is because people want to be the first to be second. They don't want to be the first to be first. And if we had just one working example in a bay someplace, and where people could come and look at it, and walk out on the pilings and look at the system floating and seeing that it's producing food and cleaning water and growing algae. And I mean, then I think a lot of people will get into this technology and the technology development.